Okay. Let it rip. Hello, everybody. Is this showing? Can we see my screen here? Hold on. Chrome. It doesn't like. Share screen. Now if I make this presentation, what happens? Okay, there we go. All right. Okay. Great. Hey everybody, welcome to another edition of the Hoot. I'm Scott Weiss, architect at solo.io. I'll be presenting today about an area we spent a lot of time working on at Solo, which is building multi-cluster operators. Oops, I hear an echo of myself. All right. So building multi-cluster operators for Kubernetes, and we'll explain what all that means. But essentially what this is going to cover is when we build operators, we write our own operators to automate processes in Kubernetes, how we can build those operators to manage multiple clusters, not just a single cluster. And we'll get into some of the solutions and architectures and motivations for that. So let's get started. So as far as understanding Kubernetes multi-cluster adoption, as probably most of you know, Kubernetes is seeing very high rates of adoption. I think in recent surveys, something like 80% or 89% of IT departments responded that they were using Kubernetes some way in their infrastructure, and a large percentage were using it in production. Most Kubernetes users are using more than one cluster. With a recent study that was released last year, a CNCF survey report reported that 28% of Kubernetes users are running more than 11 production clusters, which is a 56% increase from 2017. Basically, multi-cluster is becoming more and more important part of the Kubernetes story, seeing how we scale out our Kubernetes adoption. Also, Kubernetes isn't just being deployed multiple clusters in a single provider, a single infrastructure. We're seeing multiple infrastructures and hybrid cloud and multi-cloud deployments of clusters. So just to understand why users would have multiple clusters, the different use cases basically fall into two categories. You can have replicas of an existing cluster that may be in different availability zones. It may be on different clouds or in different and on-prem and in off-prem. But we have essentially what this cluster is running itself. It tends to be the same. The idea is that we're basically running replicas, just like we can have multiple replicas of a deployment. We can also have multiple replicas of a cluster deployed to different places. And this allows us to, for example, replicate our food service here in multiple regions so that an API gateway or load balancer could route between them. For example, based on locality, based on where a user is sending their traffic from, or based on what's available. So if one cluster is unhealthy, we can route traffic for the target service to a different cluster. So this is the homogeneous approach and use cases for homogeneous clusters. And then you have heterogeneous clusters. And the use case for these is when you actually want to have a separation of concerns that build the application within the Kubernetes clusters themselves. And this you tend to see with large organizations where they have separate platform team and application teams. So often application teams will be given their own clusters, but the resources that those clusters are privy to may be restricted, and they may have to go through an additional cluster in order to access APIs or more. This is just one example of how multiple clusters can be used to separate concerns. There may be organizational change requirements that necessitate different organizations have their own Kubernetes clusters. There may be tenancy concerns where each tenant is given its own Kubernetes cluster. There are security reasons why different services may be isolated into different clusters, but essentially these are the two classifications for multi-cluster, and we see at Solo working with customers both use cases being adopted. Depending on the organization, they may be using one or both types of multi-cluster scenarios. So running a multi-cluster setup like so, whether regardless of the case, requires us to solve two problems that come up. One is about orchestration, which is how do we actually orchestrate the resources across multiple clusters. So, when you're working with one Kubernetes cluster, you just set your kube config to target that and use kubectl apply or Helm or whatever infrastructure tooling exists in order to manage a single cluster. But when we want to manage multiple clusters, we still want to be able to use the sort of idempotent declarative configuration model that we get with a single cluster. But the naive approach would be to simply apply manage configuration for each individual cluster individually and apply it individually. And then you start to get to almost more of an imperative flow where we have to iterate through all of our configurations and apply them individually to each cluster, which many customers are actually doing today. Many users are doing today themselves by hand in their CI/CD pipelines, for example. And that's a sort of naive implementation or a homegrown implementation of the simplest approach to configuring multiple clusters. But that's for the orchestration or the configuration. And then there's the networking. And networking essentially says once we've actually configured these clusters, or once we've figured out how to configure these clusters, how do we then connect the services running within them to each other and allow cross-cluster communication? This is especially important in the heterogeneous architecture where services may depend on each other, services that depend on different service in a different cluster. There also may be a case where service is talking to a local version of another service that it depends on, but that service is replicated in the local cluster and a remote cluster. And if the local cluster one becomes unhealthy, we may want to fail traffic over to the remote cluster, which would also require this interconnectivity between clusters. So this talk is not going to go into the networking side of things. We have another Hoot covering that, and if there's more interest, it's really a very dense topic. And we could definitely, if there's interest, let us know. Send us a Hoot, and we'll, we can definitely queue up some more talks that do more deep dive in how to accomplish the networking piece. But just from a high level, orchestration today can be done using GitOps. Like I mentioned, you can just integrate your GitOps process in order to essentially individually configure each cluster, but do so in a way that's easily managed from a single GitOps workflow. Like this can be done with Argo today. Argo has cluster management. I believe Flux does as well, which are two CI/CD projects in the Kubernetes ecosystem. Another way of doing multi-cluster orchestration is actually to leverage a virtual kubelet. This is how some projects like Admiralty and Tensile Kube are doing it, where you basically have one management cluster, and then you take your sub-clusters or your managed clusters, and you consolidate them into a virtual kubelet. And you have a virtual kubelet added to your main Kubernetes cluster as a node, and it can then schedule work like pods and such onto those remote clusters. Then you have, and this is really what this talk is going to focus on for the majority, is building, basically taking the Kubernetes controller concept and expanding it so that controller can manage not just the local Kubernetes cluster where it runs, which is how traditional controllers are built, but actually that it can manage remote clusters as well. And that requires it to have credentials, some sort of external credential for interacting with a remote API server. which is different than the credential that a pod receives locally inside of the cluster. We can get more into that. Then finally, there's just a slight modification, but I felt it important to point out, because this is the new model that we're adopting here at Solo, and I'll spend a little time going over it. And this is something we could dive into in more detail in a future Hoot, again, if there's interest. But this is essentially running a Kubernetes controller in this management cluster that manages multiple clusters, but rather than having it speak directly to the API server from remote clusters, which requires sharing these credentials, we give it, we install an agent on each of the remote clusters, and then that agent does all of its local Kubernetes operations, and they cluster together using what we call the relay API, which allows a central management plane to relay instructions to an agent running on the local machine. So it can read and write resources to remote Kubernetes without needing to directly access the Kube API of those clusters. So that sums up the available approaches in orchestration. Then you've got networking. And I don't want to get too deep into this, but these are basically different ways of achieving cross-cluster networking. One is to simply use whatever your cloud provider may leverage for you. So for example, you may be able to set up a VPC for your all the VMs on which Kubernetes is deployed, and then deploy your pods on a subnet that's addressable from both, let's say both of your VMs, and essentially set up flat networking for all the pods. This really has to do with the way the clusters are set up and depends on your cloud provider and what they support. But this would allow pods to talk to each other's IPs directly. It doesn't necessarily solve the problem of DNS names and how services actually will get routed. Can do service discovery essentially, or can talk to those remote IPs on a DNS name. So Service Mesh provides some functionality there. Service Mesh also provides us the ability to reroute traffic through proxies that intercept calls that are cross-cluster and then route them through something like an ingress load balancer on a remote cluster. Then you also have various CNIs such as Cilium that you can install in Kubernetes, and those can be configured to create a virtualized flat network across segmented networks. And then you can also just use your own custom setup. You can install an Nginx or Glue load balancer inside your cluster, and just configure your services that need to talk cross-cluster to go through the ingress of the remote clusters where they want to talk. These are all solutions that we see various customers adopting today. So let's take a little bit more into a dive on the orchestration piece and how this actually works. So in the GitOps approach, we use a Git repository as the source of truth for all the configuration for our clusters. So cluster admin would push changes to a Git repository. There's some approval process, maybe a pull request gets merged, and this initiates the CI/CD pipeline. The CI/CD pipeline takes all of the configuration that's stored in the Git repo. There may be configuration assigned to each individual cluster, or there may be templates of configuration that are applied unanimously with only those templated out changes as they get applied to each cluster. But the configurations get applied, any pods that need to be scheduled, services need to be created, ingresses, service mesh configuration, etc. All of these things are prepared, and the CI/CD pipeline will leverage the kubeconfigs that it's given access to, for example, in your GitHub secrets or some kind of secure credential store that the pipeline can access, and that will have the job of running the Helm commands or kube commands, kubectl commands, or otherwise invoking the Kubernetes APIs in order to create the desired cluster configuration. One of the problems with this is that it's not dynamic. So this means that a static configuration will be applied to the clusters on a Git repo update, but the clusters themselves being updated or state changing inside the cluster. For example, a node going down, wanting to change the way, or a cluster going down and wanting to reschedule the workloads onto a different cluster is not something that is handled natively by this system. Would need more manual user intervention in order to support a more dynamic, more responsive approach. So another approach for this is we're using the virtual kubelet. So we see here that in this situation, the cluster admin is managing a single management cluster, scheduling work and scheduling resources onto that cluster. But some of those resources can get scheduled onto a virtual node. And the virtual node is created via the virtual kubelet, which essentially gets the scheduling requests from the management cluster and is then able to do whatever it wants with them, including schedule them to a remote cluster. So this is how some projects out there like Admiral and Lico are working. And it's primarily useful for scheduling work, scheduling pods, and other things that actually get scheduled to Kubernetes nodes, where other types of configuration which an admin may want to apply to a specific cluster, for example, some kind of networking or ingress, are not necessarily going to be represented by this approach. It also requires that essentially is only going to expose anything that's supported by the existing Kubernetes APIs, because the virtual node, again, is only able to claim ownership over things that the management cluster itself can schedule to it. So this is not going to support, for example, a cluster admin wanting to configure a specific cluster being managed. Again, it depends on how the virtual node is implemented, but in the existing solutions out there, we mostly see this being used to manage scheduling pods or other types of workloads like VM workload. So let's take a look at the multi-cluster controller, because I think this is the most conformant with what we expect from in a Kubernetes ecosystem. The way we like to work with things is to have a single declarative configuration file that can then be applied to ensure a desired state in my infrastructure. And as whether or not that's a single Kubernetes cluster or multiple Kubernetes clusters really should wind up being an implementation detail at the end of the day. And that the API that the admins want to work with is one that allows them to declaratively configure any number of clusters. So in this world, the user installs a controller into a management cluster. They also have to provide a set of Kubernetes configs that give access to remote clusters. So we can talk about where those Kubernetes configs come from, because, for example, the cluster admin can just upload their own, but those may be privileged that we don't want to give to the controller. So what we'll often do is we'll provision a service account on the workload cluster. Then we take that service account and we bundle the service account token into a new kubeconfig. And we ship that kubeconfig back to the controller, where then the controller can access it. And now that kubeconfig is constrained by the RBAC that we've applied to the service account that lives on the remote cluster. So it still allows us to work within the constraints of the Kubernetes ecosystem, but unfortunately it does require us to transport those credentials outside of the cluster where they're provisioned. And it's essentially exposing the Kubernetes API to additional external clients, which increases the vulnerability surface of our cluster. But this is nice because it allows the controller to dynamically synchronize the state in a continuous reconcile loop, as the controllers we talk about are, or this is like the community nomenclature for the behavior of controllers, that they perform a continuous reconcile loop when they receive a state change. It also allows those controllers to implement new APIs which address multi-cluster use cases. For example, a cluster admin can provision a CRD, which requests a service mesh or an orchestration component to flatten the network or create a bridge network between a set of workload clusters to enable cross-cluster communication. And then the controller can go and individually assign the service mesh config to a mesh running on each cluster, which can then bridge them together. And finally, just to review the updated approach to this model, to the multi-cluster controller that we've begun implementing here at solo.io. Rather than having the controller directly access the remote clusters via a kubeconfig, instead we join an agent that runs on the remote cluster back to the controller using a shared root of trust. So in this model, we don't need to provision a new credential on the workload cluster and then ship it back to the controller. We simply need a common root of trust between the controller and agent, which can be a TLS certificate with a shared root, which they then use to identify each other, establish trust, and then establish communication. So one of the drawbacks to this approach of the multi-cluster controller using this model is because we first have to provision a service account on the remote cluster and wait for the Kubernetes API server to actually then create a token with a set of permissions and that identity in the cluster, it makes it impossible to register clusters via a declarative mechanism. So what does that mean? That means that I can't just Helm install one cluster and then Helm install another. What I really need to do is I need to do some process to create a service account on the workload cluster, fetch the token that Kubernetes generates for it, and then ship that back to the management cluster. And that flow is, it's an imperative workflow that currently requires some either scripting or using a tool like, we can look at one of the tools that, if there's some interest, we can take a look at it. It's called the Kubefed, which is one of the popular implementations of a multi-cluster controller that's designed for sort of generic use case, which is like I have some YAML, I want to distribute across clusters. You use the Kubefed CTL CLI command in order to join the cluster, and it orchestrates that flow. But one of the advantages of this agent workflow is that the agent just comes online, it's given that client certificate to talk to the controller and establish its identity, and it simply just connects and then begins managing its local API server. So there's no need for an exchange of credentials, there's no need to provision something, wait, and then manually ship that into a different cluster. That would be one of the advantages here. Another advantage is that the agent can do pre-processing of resources and data, so that if the controller wants to watch something or do a read on the remote cluster, it can request from the agent only the subset of the minimal subset of resources that it needs. And the agent can parse down that data into something more lightweight. Almost think of like a GraphQL API in a way where you can just request the data that you specifically need rather than fetching the entire tree of objects or list of objects. This is particularly useful when you're talking about really large scale, lots of clusters, like 80 clusters, hundreds of clusters, because network bandwidth actually begins to become a significant concern. It's also a technically more secure API because the API is exposed by the controller, the agent subscribes to it, the controller only allows a limited set of APIs that the agent can invoke, which means we can further restrict the kind of access that's being given to the remote API server. This also means that Kubernetes credentials for the workload clusters never have to leave the cluster. They only stay there, and our agents are, when we audit the interactions with the API server, we only have to look at the agent in order to understand who made those requests. This does have some downside because there's some additional bootstrap in order to get it working. The agents have to be able to talk back to the management cluster, which means we have to have a secure ingress set up. It also introduces the agent as an additional point of failure in the system, so it becomes one more thing to manage and to debug. But for us at Solo, we've seen this, the trade-offs paying off here, and we have customers who have security requirements that don't permit them to use this original model. So that sums up the architectures or approaches that exist today in the ecosystem. And let me ask if there are any questions first. I don't know if I can get questions here. I'm not sure if we got any. Let me check. No questions. Okay. So as far as a demo, it's I really wanted to leave it up to the audience to decide what you'd like to see, because there are a few options. One thing I could do for you is demo Kubefed and actually show what it looks like to put some config on one cluster and move it to another. Another thing is this talk is about building controllers, so I can actually show you what it looks like to write a controller. We could do it in Go using the controller runtime library, which is what we use at solo.io, and show you what a multi-cluster controller would actually look like in terms of the code. But I'd like to gauge from the audience if there's any what your interest would be. And then we can take it from there. It depends on the type of the type of thing that you're looking for here. We could also there's some more slides I have here on the security constraints and why we're going with this new approach. Although I think that it's probably better suited for its own talk, so we can get into the deeper technical details. But if there's no interest or there's no specific request for a demo, why don't we let's see, here's one. Okay, very cool, very cool. More interested in writing the multi-cluster controller. That was what I figured would be more interesting, because trying to leverage tools from the community, from the ecosystem, is it's probably the first avenue that's worth investigating or considering, depending on the use case. But in this scenario, we want to write a generic controller that's going to my OBS is freaking out a little bit here. Yeah, so let's take a look at what writing a multi-cluster controller looks like. So let's see now. See if my Golang comes up. It's bugging out. It is totally bugging out. It's OBS, it's not me, I swear. What is this? It's flickering. Okay. I got the size right. Can we stop flickering? Why are we flickering? What is this? How are we doing? We okay? I'm sorry, everybody, for the interruption. OBS is being totally weird. Stopped. Okay. Well, let me know if it starts again. So let's take a look at this from the top down. So just for so I've created a little project here that we're going to work in Go. This is, if you're not writing your controllers in Go, the ecosystem is much more limited. It's definitely nice to have this controller runtime here. So the first thing that what we do when we start we'll just write like a basic controller. The first thing that we do First thing that we want to do when we create our controller is we want to connect to the local Kubernetes cluster. So we need a config, and this controller runtime library offers that to us. And let me just show you. It's this controller runtime here. You just do go get SIGs solo.io controller runtime, and that'll get it for you in your local Go project. Then you get a config. This is called a REST config. This is basically your Kubernetes config. It can get loaded into, and in the if this is running on your local machine, it'll use your Kubernetes config, and if it's running inside of a pod, it's going to automatically load it from the service account credentials that the pod has access to. So you can see they have this in-cluster config. See, it reads it from this file inside of the pod. So anyway, this REST config is going to become important in a second. But right now, when we run this means we're getting it either for the cluster that we're living in or the cluster that our kubeconfig is pointing at, if we're running on our local machine. And this is what we're going to treat as our management cluster. So we're going to take there's this thing called a manager, called MGR. Manager is it's basically the interface that controller runtime gives you for interacting with a Kubernetes cluster. And there are all these options here. I'm just going to leave them all blank for now. If we look at the manager interface, we can see what the manager has for us. But essentially, we can get a client for interacting with the cluster. We can get a cache of the objects that we've been watching on the cluster. We can, these are just different types of clients. I mean, that's basically it. That's really all we really need here. There's more to it than that, but or there's more that the manager exposes. But essentially, I get the client, we get the cache. Between those two things, you have pretty much everything you need to build a controller for most use cases. But anyway, we create a manager. Now this essentially allows us to start watches on things in the cluster as well as to write things to the cluster. So let's take a look at a watch, because that's really what our controller does. It starts a watch, and it reconciles the things that it watches. So the next thing that we do is we're going to create a controller. Do controller.new. Any day now. How's the flickering? Are we flickering? No flicker? Okay. You know what? I'm just going to put this up on something here. A little better. There we go. All right, so we're going to get a controller. We can give it a name. Very creative. Options. Cool. Again, I'll just show you the options here. We're going to ignore all of them. It wants the manager too. My bad. So the controller is going to basically inject itself into the manager as something that it's going to run our reconciler. We'll show you. We'll show you what this means. If we look, the controller.new calls manager.add on itself. It adds itself so that when the manager gets started, the controller will get started too. Nothing too interesting. It's just turn on error here, turn on error here. Okay, now this controller, I don't think that we actually have to do anything with it. We can just, oh yes, we want to watch, that's right. So we created a controller, and we're going to do a watch with it now. Let's watch return, just an error. All right. So we have a watch here. It's going to take a source. So you can make your own sources. Source is basically a source for events. It tells the controller runtime how to feed events into your reconciler. That'll call the reconcile function, which we actually haven't defined yet. It's going to go right in here. But let's figure out what we're reconciling first before we figure out how we're reconciling. So I'm going to put in this here, source.kind. And this is a way of now I'm confused. Oh, that's right, that's right. There's this, it's a little confusing. It's handler.enqueue request for owner, I guess for object. I can explain what each of these is. So source.kind, type, let's do v1.config.map. So now we're creating a watch on config maps here. And we're telling the controller, watch config maps, and when a config map comes in, it enqueues a request. And the request that it enqueues will be for the object. All right, so what's a request? A request is a reconcile.request. It's the most basic thing you can imagine. It is a namespace and a name. So we don't even have a type information associated with this. So what happens is we're going to start getting requests that have a namespace and a name of a config map. And that's essentially what this says. Watch config maps and then generate a request that is the name namespace. You can see it right here. It adds to the queue every time there's an event, like a create event, an update event, or a delete event. And to be clear, this refers to the event is what happens when the controller's cache that's running locally synchronizes an event from the server. So the server says, I have 4 config maps. And then the client, the controller here says, okay, I have 4 create events because an object just got created inside of my cache. And every time your controller gets restarted, it'll get create events for every time its cache becomes populated. So just to be clear, these events track what happens in the client-side cache. That's important. It's not what's tracking on the server. And there's no guarantee. It's guaranteed to be eventually consistent. So, for example, if an object gets created and then deleted very quickly, we don't know, we may never receive any event at all. Or if an object gets deleted and then created very quickly, we may also not receive an event. It's just eventually consistent with what's on the server. And that's important for how we design our reconcilers. How's everybody keeping up so far? Does this all, have any of you seen this before? Does this make sense so far? I know it's a little complicated. So far we've gone over the manager. the controller, and now setting up a watch with the controller on the config maps. Let's see. Any replies? No replies. All right. I'm going to move along then. So we've set up a watch. Now, what's going to happen when our cache picks up a config map? Well, we haven't decided that yet, because this reconciler here, we haven't defined. The reconciler defines the function that'll be called, we're slowing down again. I think it's the new MacBooks. They don't have the processing power to handle something like OBS and Golang at the same time. It's I think we're coming up on bottleneck. I have to ask the company for a new laptop. That's the real. I need like a extra couple of gigs. Imagine if I was running Minikube. It's buffering. Uh-oh. I think it's my machine. OBS. It's OBS. How are we doing? Better? Sorry, let me continue. Okay. All good? Can we hear? All right, so this reconciler here is what's going to be called when we enqueue events. It's going to receive these requests. So we have to define the reconciler. You'll see reconciler reconciles an object. What's the interface? The interface is just a single function reconcile, and it gets this request object. So let's take a look at what that looks like here. I'm going to define a type, my reconciler. Just going to blow away all of this. And that reconciler, we're going to have it implement the reconciler interface. Cool. And this is now what it does. And we can just put, if we want to, very lame. Now I know this is very basic. We're not quite up to the multi-cluster stuff, but I feel like it's important to start with this as a foundation. So now we have a reconciler defined, and we can just pass that in here. Let's initialize it. Here. Now we have a reconciler. Now this should work. There should only be one last thing to do, which is return manager.start. Do context.background. And this should be good to go. I'm going to put one more log line in here, just to make sure we're not crazy. We should even be able to see metrics for it. If we put a metrics bind address here, let's do 1, 2, 3, 4. Now we start this process. Yeah. Doesn't like when go mod tidy, maybe we just make sure the go mod's happy. No auth. It's the old auth provider. My favorite. My favorite. This is something that you know, you'll have to explain to me why you have to do this import. But let me just pull that up really quick. I have to like look at one of our repositories to remember this line. It's, you see this no auth provider found for name GCP? This basically, you have to import some auth plugins. There it is. I'll show you. It's this. You just import this guy and you're all good. Then you can connect. This is so that you can connect to various. Oh my god, what is this? Go mod download. Work. Work, I say. 1 second. Charge it back in. There we go. All right. Please work. It's taking a sweet time. Okay. A missing port in address. Oh, you're kidding me. Port. It is a port. I wanted to show the metrics. All right, now you see we are cache synchronizing here and we're receiving, first we get every single config map that exists in the cluster, and then you'll see some of them are getting changed. They're probably, you see these are locks. A lot of the time different components will use config map actually as a locking mechanism, so they update the annotations. And let's take a look. We can actually, let's take a look at this ingress GCE lock, for example. So if I get in the kube system namespace, what was it, GCE data election or something? Ingress GCE lock. Oh man, this is going slow. This thing. It's the Mac. Yeah, it's just this Mac. It's this kernel task thing telling me it's overheating. Yeah, I apologize everybody, the technical issues we're having here. Alright, hopefully I can find something to prop. Let's see. Hopefully this will do. How we're doing. Okay, it should be better now. So we get the config map, the ingress GCE lock here. When we watch it, it looks like it's getting updated continuously. So see where, yeah, leader. They're using it for leader election. You see? Data transitions. One of these is updating. Yeah. So anyway, you can see that our system is now watching events. Cool. One last piece that I think is worth noting is how we can actually act on them. So we receive this request. We know it's config map update. what do we actually do with this? How do we, if we're watching like my custom CRD or we're watching config maps, how do we know to actually do something? So that's where we want the cache. And this is where, this client, something like that. So basically what we want to do is we want to give this, my reconciler here, access to the manager cache. I think it's just going to be the client. I don't think we want the cache. The client reads from the cache. Oh wait. Okay. It's client.reader is really what we want. But that's fine. Now we just do cache is client.reader. Now, what we do here is we can now fish the object out. You say cache dot, m dot cache dot get, and we fetch the object from the cache. We do the context. We have a key. So the key is client.object key, and is literally just request namespace and the request.name. Now we fetch the object. Oh, and the last thing is we need an instance of the object to populate. Oh, we have a config map here. Config map. And we just stick that right in there. So now, what happens if we try to read it and the error is not nil? So there's a case where this is actually valid. And it's if, no, it is not, yeah. So if it's a not found error, it means the object was deleted. I'll just put a log line in there. Config map was deleted. All right. Return. And otherwise, if it's not that error, it's some other error that should never happen. We'll return the error. But if we got to this point, it means the config map was updated or created, and we can get access to the data. Like so. So let's restart our controller here. So far, how's everybody finding this? Does it make sense? We now have a controller that's watching config map. Oh. Someone's storing a TLS certificate in a config map. Uh-huh. And anyway, we can now see that we are looking at our config maps. We can get the data out of them. We can act on them. If we want to write something to cluster, let's just add a client.writer. We want to create some new objects. So we just quiet chat, yeah. Well, anybody interrupt me if there's something here that speaks to you. So now we have a writer as well. All right, that sounds good. New M1 processor. Probably. They're brutal with these things. All right, well, just ping me if there's an issue again. Hopefully it'll be stable. All right, so for example now, we can write, if we want to, you know, in our loop. So maybe we have something like, we're going to create, I don't know, something totally different. I want that every time we get a config map update, I'm going to go update, I mean, a config map seems like the logical thing. Let's do secrets. So I'm going to change this now from config map to secret. So we're watching a secret. Watch a secret. Now we're watching secrets. And what we'll do is we're going to manage a config map now. And let's say we'll create a config map that has a list of all the secrets in the cluster. You know, not a super exciting task, but something that a reconciler is well suited to do. So we'll do this, repeat this block over here. Let's update our secret list. So it's a config map. And the config map, we're going to have a fixed name and namespace for this. So we'll put in the default namespace, and the name is going to be called secret list. And now, if it's not found, we're going to create it. So we're going to do m.writer create context. We need to make sure our name and namespace are set properly. Let's do that. Oh, whoops, I got this mixed up. Now we're going to create that CM. If it errors, we'll return. If you return an error, the controller runtime library will automatically requeue the event, so you can try to reprocess it later on. So we create it. Otherwise, we don't return here. Else we return. So that way now we've created it. This create method will also patch this object with the resource version so we can then update it. Now we say okay, cm.data, and we're going to put an entry in there with we'll say we'll take the request.namespace, and we're going to append here. The data is a byte array, not data. Oh yeah, the config map, it's a string. So we're just going to do just to make our life simple, we're just going to put the whole request.name. Namespace is a key in here. Equals, you know. Something. We'll just have it a fixed character. All right. So now we've updated our. We set the data that we want. Now we can use our writer. And update. And we can just do that on the end here. And now every time we get a secret from the system, we should go and update this config map with a list. So let's go run it now. Oh, hello. Panic? Oh, because it's empty, because the data is nil. Let's if cm data is nil, cm.data equals a map string. Oh, there we go. Down here. Now check this out. Let's say now we deleted the secret. Oh, do I want to start talking about multi? Yeah, it's true. It's true. It's true. Maybe I'm getting off topic here. All right. The point is that now I should be able to see that we have a controller that resyncs things. Let's just run it and see that this is operating within the scope of one cluster. I think maybe we're getting a little bit to the limit for a single Hoot, and maybe it makes sense to do a follow-up where we do more of a coding session and actually look at writing one of these things. I hadn't planned to go this long. Just why doesn't it like me? Doesn't seem to be doing anything. Yeah. Okay. I think that that's good enough on the multi-cluster. I think I will try to schedule another session where we can do a little bit more on the coding and actually show how to connect this to multiple clusters. But essentially what a multi-cluster controller is doing is it's reconciling these requests, but not just from a single cluster. We're able to watch all the clusters. And then we can build essentially a snapshot of all of our resources, of all of our clusters, on all of our namespaces. And using that, we can then drive the configuration for all of our clusters. So I'd like to show everybody this approach, but I think we're pretty much at the time limit for this Hoot. So stay tuned, and I believe in a future episode we will get a chance to do that. Thanks for watching.